Good. Hey, everyone. Thank you for coming to this room today to attend this talk. Uh, I'm Nikunj. I'm in the M3 team, and we're located in New York. And today, I'm going to talk about how you can go about building your own metrics pipeline. And I'm also going to give some insight into Uber's production metrics pipeline. So I hope you are all ready for it. Cool. So yeah, I'm going to briefly talk about metrics at Uber, how they're interesting, and then talk about M3, which is our metric stack, and finally about how you can use all existing open source tools out there to build your own metric stack. All right, metrics at Uber. So Uber has a lot of microservices, and at a very high level, you can think of a microservice as some end user code, which is like the business logic and a bunch of libraries. So we have a lot of libraries for our RPC framework, and then the services can use libraries to talk to storages. So our RPC framework is kind of interesting because it emits a lot of metrics automatically for users. So users don't have to worry about figuring out what kind of metrics they need to monitor their services. The libraries do that for them. So this is kind of an example of a dashboard, which we actually automatically generate. So based on the service, we kind of figure out, oh, this is a Mesos service, so we give them a Mesos dashboard. We see that they have Cassandra, so we give them a Cassandra dashboard. Redis, so give them that. So a lot of times what happens is that service owners are not experts in some of the calls they're making, so in some of the storage technologies, so we give them the right set of metrics for them. I'm going to jump into one of this section. Yeah, Muttley. So Muttley is our internal routing framework, and this is what we use to route from service A to service B. And Muttley gives out a bunch of interesting metrics. For example, for a given service, you can see all the calls it's making to its destination services. You can get kind of the success latency distributions. You can get errors, throughputs, things like that. And usually in production, whenever there's an outage, there's a big problem that only the service owner knows about the kind of metrics that service emits. And for a non-service owner to figure out the root cause an outage, if it's outside their service, it's kind of hard. So this way makes it so that everything is consistent. So you can just follow your dependencies of a service, and then you can see which may be causing a problem. I mean, obviously there are other ways to do it, like you can do tracing and things like that, but this is like one of the ways to help you out. Cool. So now I'm going to talk about why serving metrics at Uber is a hard problem. Okay, talking a little bit about our scale. So we ingest about 400 to 700 million pre-aggregated metrics every second. And if you think about it, it's actually a lot. I mean, it's probably around the scale of like Facebook and Google at this point, which is very interesting because we're a much smaller company than theirs. So these are all the raw metrics which we get from all hosts at Uber. We then aggregate them into based on what kind of rules users have written for aggregation. We also have a bunch of default aggregation rules. So you can do things like, oh, I want a particular metric at 1 minute resolution. So we would aggregate that metric over 1 minute time windows and send those to our storage tiers. So after aggregation, we actually reduce our number of metrics to about 29 million every second and send it to our store. It's still a lot. It's like 50 gigabits per second. So that amount of scale means that we need a solution which can, scale out very easily. Our data has very high cardinality. So we have about 9 billion unique metrics, which kind of poses a lot of challenges, both to the store because the index has to keep track of so many metrics, and also during fetches. So now when you write a query, there's a high chance that it matches a lot of metrics. So there are other systems out there which kind of prohibit high cardinality metrics. So they kind of say you should do all pre-aggregation so that your cardinality is low. But in our experience, it's very hard for you to know what metrics you need. So it's very hard for you to figure out what pre-aggregation rules to write. So yeah, that's why we let people do whatever they want, and which results in this high cardinality. Talking about the query side, we have about 2.2 thousand queries run every second, and most of them come from our Grafana dashboards. And we also have an internal real-time alerting system, and some of the queries come from there as well. This is another view to see the same thing. So some queries can be small, others can be huge. End of the day, we are doing about 8 billion data points every second. So I'm just trying to show how we're just pumping massive amount of data in and out of the system every second, essentially. This is kind of a moving target. So when we looked at how the system was adopted, we were actually kind of pleasantly surprised at the growth. So the persistent metrics, unique IDs have been up by 50% in the last year, which is like 2.25x growth every year. Our QPS for query service has increased by 100% since last year. And our overall ingress traffic is like 90,000% in the last 3 years. I mean, this is mainly because as our stack gets better, more people try to adopt it. And the more automated things we build into it, the more the usage grows. So we have a moving target, which we had to chase while designing our metric stack. And that's why we had to build a system which can scale out easily without much manual interventions or manual sharding, which some other systems require. I'm going to talk briefly about M3, which is our metric stack. So this is kind of like the high-level architecture for M3. So think about an application. It runs whatever code you write in it, and then it has a M3 client, which emits metrics to M3 collector. What we recommend is within Uber, we run M3 collector co-located to the host. So every host at Uber has an M3 collector daemon running, and the application just emit the metric to its local daemon. M3 collector then forwards the raw metrics to M3 aggregator. So M3 aggregator is the aggregation tier, which I alluded to. So it looks at what rules do you have set up for this metric, and it does some roll-ups based on those. Once those metrics are aggregated, it sends those aggregated metrics to M3DB, which is our data store, and then metrics are saved. On the query side, people usually query it through Grafana or our alerting engine. They point those to M3 query service. So M3 query service looks at the query expressions, and it figures out what raw data you need, and then it will hit M3DB to get that raw data, and it applies any other functions over it, and then finally return the results. So this is a very basic architecture diagram here. Like, I didn't go into a lot of details, but there are things like, for example, Uber is running in many regions, and you have this stack in every region. And there are some use cases at Uber wherein we want a global view of the whole system. For example, we want to look at how many trips are happening across all of Uber. So for that, we need data to be available everywhere for metrics. And there are kind of two ways to go about it. One is during writes, we can replicate the data, so which is what a lot of systems do. However, at this scale, the data replication costs for us were like too high. Also, users tend to write a lot more metrics than they're reading it. So we made a call to actually do read fanouts. So when you hit M3 query through Grafana or your alerting engine, we actually fan out on reads to all the data centers which match the query. We get the data and we consolidate it and then apply the functions. So that's kind of different than usual data stores. Cool. I'm going to dive a little bit into M3DB. So M3DB is our open source distributed time series database. It lets you store arbitrary timestamp precision data points at any resolution or attention. one big thing we noticed, like, so before we built M3DB, we actually used to run a Cassandra stack. I mean, we never wanted to write our own database because that's not really fun. And it's like a little hard. So we actually started out with Cassandra first. So we would store our metrics in Cassandra. But we as our Cassandra clusters grew, we started seeing problems maintaining such large clusters. Like we tried to manually shard those clusters, but they still became big and they will take forever to add a node or remove nodes, things like that. And then we also saw big problems with compaction. So whenever a compaction will run in Cassandra, we'll see like nodes are jumping CPU, the latencies will go high, things like that. So this was one call we made, was that we will not have any compaction in MTDB, just so that our system profiles are stable. Thirdly, data is replicated, and the number of replicas is actually configurable. And I'm going to talk about it a little more later. And finally, we rely a lot on etcd to provide cluster membership. So every node is talking to etcd, and it has a strongly consistent cluster membership model. Cool. So as I said, we initially used to run Cassandra, and that happened until 2016. And these were the numbers which we came up with. So once we started having problems with Cassandra, we actually started building our own database, M3DB. And initially, obviously, we just didn't switch out Cassandra. We were first looking at what the differences are. So we ran M3DB in shadow mode while Cassandra was still serving our production traffic. And these are kind of some of the statistics we saw. So M3DB beat Cassandra by a lot in all, P50, P95, P99 reads. So it was really fast. Cassandra was super expensive, and that the main reason was that M3DB can achieve a lot of compression using the property of the data. And I'll talk about it in the next section. But so M3DB proved to be really cheap, like as you can see in the graph. Since Cassandra was expensive, we were only able to use a replication factor of 2, and we were not comfortable because for a quorum, you need at least a 3 replication factors. So, but once we moved to M3DB, we were able to bump up our replication factor as well. However, it still proved to be cheaper. So the main idea, like the main reason why we got all this was because of the compression algorithm. And we don't really claim to have designed a novel algorithm or anything. It's Facebook came up with the paper about GorillaDB a few years ago. And most of the modern time series systems which are used for monitoring actually borrow the same algorithm, and they tweak a little bit. But the basic idea is that a metric is essentially a timestamp and a value pair, and both are 64 bits. However, if you think about how metrics are emitted, they're usually emitted over a fixed interval of time. They're usually fixed intervals. I mean, they can be slightly different, but it's usually pretty close together. So if you look at the deltas between 2 times of metric emissions, they're almost similar. And if you look at delta of deltas, they're pretty close to 0. So in this example, our algorithm can actually encode delta of deltas. And if it's 0, it just uses 1 bit instead of 64 bits. So this is like kind of an extreme case where everything lines up. Even if it didn't, it still wouldn't take 64 bits. It would be like a few bits. So that's how we can achieve like a lot of compression here. Similarly for values, usually metric values don't change that much over time. If they do, fine, then we get less compression, but at least in our experience, we have been able to get a nice compression ratio using this algorithm. And these are kind of the numbers which we got from our system. So as I said earlier, we used to run Cassandra until 2016. And these are like, so Cassandra, we did replication factor of 2, and it used about 1.4 petabytes of disk. With M3DB, we were actually able to increase our replication factor and still get an order of magnitude lower disk consumption. So this was a pretty big win for the team. And this was kind of testament. And then we started to completely replace our Cassandra stack and launch M3DB internally. And we soon realized that even though we borrowed the ideas from the Gorilla paper, they haven't really done much work towards it, especially towards making it open source. So that's when we realized that there's no tool out, no database out there which kind of solves this problem. And almost every company needs a monitoring stack. So that's when we started pushing this into open source. Okay, now M3 Query. So M3 Query is an open source query engine for metrics. It supports PromQL, which is kind of popular in the open source world, and M3QL. So M3QL is a language we built internally at Uber, which is a little bit more feature-rich than PromQL. M3 Query is interesting because it supports extremely high cardinality queries. As I said initially, a lot of systems kind of discourage having very high cardinality data, and they say use pre-aggregation rules. But we allow, like internally at Uber, we allow queries which can match up to 100,000 series. So essentially, the problem is that the more series which match, the more memory you need temporarily to process those queries. And that's why all those people are limiting the amount of series so that they can still work in a sane fashion. Now, since query does read fanouts for multi-data center queries, we have optimized it by using some compression properties of the data. We have a columnar data model, which allows us to do parallel execution for functions, and I'm going to touch on that in the next section. We do just-in-time decompression, which helps us to reduce memory footprint. Some people would say massively reduce memory footprint. I'm going to talk a little bit about that as well. And finally, so this, a lot of UI systems have to downsample data when they actually display. So if you think about fetching metrics for even a week, if the metric has 10-second or a minute resolution, there are a lot of pixels which need to be displayed on the client. There are two problems. One is the client may take forever to render those pixels, or it may be very memory intensive, like to render those pixels on the browser. And then, so what systems like Grafana do is that they actually calculate how many pixels you have on your monitor and how big your window is for that graph. And they actually come up with a number and they send that to the backend. And they do that for everybody. Like, it's nothing unique to M3 Query, but all the query engines will use that number and it will downsample their results to that number using like time windows. And most of them use averaging, but we actually did some work as to what's the best way to display it. And we found that this algorithm, which is like largest triangle 3 bucket, is much more, much better to show that kind of data. And I have some graphs there, like you can check it out for yourself. Cool. So a little bit into the data model. So what we realized is that most of our functions are actually applied across series for a given time. So we have things like sum, count, clamp. There are a bunch of functions. Initially, we were storing series row-wise, but then after we had that intuition, we started storing them in columnar fashion. And storing them in columnar fashion helps with the data locality, because if you're storing it row-wise, then you have to constantly have cache misses as you keep moving across time. So this was really good for our data locality. Second thing we did was to split data into blocks. So blocks is like a chunk of time. And the advantage here is that we realized that a lot of functions are actually can work independently on each block. So think about count. So a count can actually work on block 1 independent of block 2. So that way you can achieve a lot of parallelism there. So this was a way for us to kind of make it faster, a little bit faster through parallelism. Okay, now just-in-time decompression. So one of the main bottlenecks in the query service is memory. We were never bottlenecked by the CPU. The main problem was you have this highly compressed data, which comes from a database, you decompress it, and it's like you're matching like thousands of series, and then you apply functions on it. So you need a lot of memory to store that data temporarily. So I have this example here. I hope it's visible a little bit. Okay, so in this example, imagine you matched 10,000 time series, and this is over a 2-week period. So you have two functions to apply here, a clamp and a sum. Now, the traditional approach which we used initially was to first get the data from the database, decompress it, and populate all those 10,000 time series. So we had to allocate memory for that. Apply a clamp operation, then create the eventual representation, which was, again, we can probably reuse this previous one if you're smart, but we still needed that whole representation again, and then finally apply sum. So sum is interesting because it's an aggregation operation, so it reduces the number of rows. So you're summing across series, so it generates one row, and then you have each column represents time here. So even though your final representation is really small, due to the intermediate representations, we kind of calculated and you needed about 1.6 gigs of memory just to do this operation. And it's a very simple example. So if you think about matching 100,000 time series, suddenly you need 17 gigs of memory. And this was a problem for a long time for us, and that's why we were memory bottlenecked. So the approach on right shows another way of doing it. So when we see an operation like clamping, we don't apply it right away. We add it to our execution graph, and we keep doing that until we see something like a sum. We know sum is an aggregation operation, so it's going to reduce the size of our data. So what we do is we get the first column. We allocate a slice for the first column. We apply the clamp and then the sum, and then create the final representation of the first column. Then we reuse the same slice to calculate the second column, and then apply clamp and then sum, and then generate the final representation. So the whole idea is that we can reuse one single column slice for the whole thing instead of creating a full memory representation of all our data. And through that, we can save a lot in terms of our memory. So in this example, it's kind of extreme, but in this example, we would use 250 KB of memory versus 1.7 gigs of memory. So we can scale out a lot on modern hardware if you were to use this approach. And this works on a lot of functions. There are some functions which it doesn't work, which rely on different blocks instead of being independent of blocks. But this works really well for most of our use cases. Cool. Now, talking about downsampling. So I already kind of explained why UIs need to downsample, and this is true for every UI, not just for metrics. I mean, even Google Finance and those things. So we actually used to do averages. So the graph at the top shows no downsampling. So it is like very rich data, but it took forever to render on my UI, and also kind of made Chrome slow for me. So second is what Grafana's default behavior is, and what most UIs do is they tell you that you need to display less number of points. So the query engine will do averages and give the data. Now there are two problems here. First, averages actually make it smooth. So you kind of lose the anomalies in the data. And for the metric system, anomalies are probably more important than seeing a smooth graph. The second problem is that since you're averaging, now you're creating points which were never in your data set. So you can never actually refer back. Like you cannot trust the values of those points. So then you're saying that you just are relying on the shape of the graph, but even the shape is incorrect because you're hiding the anomalies. So it's worse in both regards. So we didn't come up with LTDB again. Like we don't come up with most of the stuff. We just look at the literature and figure out what's the best way. So there was a guy whose MS thesis was to see how to do downsampling properly for graphical visualization. And that person compared averaging with mode median. I mean, he had a lot of algorithms he compared, and he claimed that LTDB was proved to be very the best for displaying data. and the arguments given were that it kind of preserves the extremities. So the way it works, it is very intuitive. So the way it works is, let's assume you have 2 points already, and you have to pick the next point. So let's say you have a lot of candidates. So among the candidates, you choose the candidate which generates the largest area of the triangle. So if you already have 2 points and you have to pick the third point, you keep checking what's the area of my triangle using each of those points, and you pick the point which has the largest area. So using that, you kind of pick the one which is the most extreme. And so the advantage is that A, you're not smoothing out the data, you're actually maintaining the shape. And B, all those are real data points, like you're not changing the data. So if you look at it, like the bottom one looks kind of similar to the top one, but it's using way less data points. So yeah, that's something also which the query engine does out of the box. Come on. If I can move this. Okay, cool. I hope I didn't miss. Okay, cool. Now I talk about, I hope I gave you some insights into why Uber Scale is kind of challenging and what we are trying to do. Now I'm going to talk about, I guess, something which might be interesting around, like, if I had a company, like, how can I design my own metric stack? Cool. So if you have a very small metrics, like if you're just starting out with creating a metric stack, what we recommend is just use Prometheus. So Prometheus is an open source monitoring system. It's pretty easy. It just gives you a single binary. You run that binary on a box, and you use their client libraries in your service. Binary takes a config, and you point it, where you tell all the locations of your services, and then it starts scraping metrics from your services. So it ingests all those metrics automatically, and then you can point your Grafana dashboards to Prometheus, and then you can get the nice visualization. So it's just one box which does everything for you, and it's like a great way to start out. And that's why it's like the most popular system out there today, like for companies of small scale. Obviously, if you have one box, what happens if the box goes down? That means like you just lose metrics. So the way they solve it is that you run 2 boxes which are doing the same thing. And if one goes down, you switch to the other. And if the other goes down, hopefully you can switch back to the first one. So this works great. It's easy. But it only works as long as you need limited retention, have low cardinality, and low read writes, because at the end of the day, you're bottlenecked by that single box. And they actually had to place a lot of limits around everything, around your read traffic and write traffic, so that you don't blow up that box. So there's just another way to see that. So if you have an application, just point it to Prometheus, point Grafana to Prometheus, point, they have this thing called Alert Manager, point that to Prometheus, and everything works. So even though we built M3 in open source, like personally, at least I feel like this is like the easiest way to get started. This is the other one which I talked about. So if you want to be reliable, just point 2 Prometheus to your application, and you can have Grafana point to one, and then manually move it to the other one if there is a failure, or use like a load balancer. And then you can have Alert Manager point to both, and Alert Manager kind of does the deduping for you. This obviously has a lot of problems. There was one problem with somebody, as companies use it, people used to point out, was if one Prometheus dies, you move to the other one. Sometime later, you have to move back, but then you have gaps, because the first Prometheus will never have that data. So you can have gaps in your graphs. But still, it works really well if you're just starting out, and if you want to get basic insights into your stack. Cool. This was the issue filed in Prometheus, and it was like pretty early on. It's like issue number 10. So people, as they used it, they quickly saw that, oh, we need like longer term retention, because if you're just being able to retain your metrics for 2 days, that's not really super useful. So what Prometheus people did was, instead of making it harder and somehow trying to make it distributed, they actually added what they call remote read-write interfaces so that you can plug in other storages to make it, to increase the retention. So this is how their remote storage interface looks like. So whenever Prometheus gets a write, it writes to its own database and then also forwards the write request over the remote write API to remote storage. And you usually need a bridge to convert between this format to your remote storage format. Similarly, when Prometheus gets a query, it will execute that query, figure out the data needed, and it will get that from the remote storage. And then Prometheus still owns the responsibility of applying any functions to that data. Cool. So the approach we took was that you should be able to still Prometheus because it's so simple, but expand it through M3. So if let's say you had your small company and you started out implementing that single box Prometheus, and now you're like, I need longer retention, then you can use this M3 coordinator sidecar process. So it is a very low, lightweight process which you can run on your Prometheus box. And you can set it up as remote read write, and it will forward all those metrics to M3DB during writes, and during reads it gets from M3DB, and this lets you have any amount of retention. So M3DB is clustered, so you can add any number of hosts and get any amount of retention. I mean, at Uber, we have some use cases where people have 5 years worth of retention, for example. Cool. So with M3, we had this philosophy that instead of just pushing this completely new stack into open source and forcing people to learn about it, we wanted to be plug and play with Prometheus so that people gradually learn about it. So as I mentioned earlier, to increase retention, you can use the sidecar and seamlessly interact with MPDB. You can see how well it works on your production loads, and whether it be a good solution for you. And there's no real downtime because you can just shadow it, things like that. Once you, as I mentioned earlier, Prometheus still owns the responsibility of applying all those functions. It only gets the data from the remote storage. So the query engine of Prometheus is very limited because they don't want to blow that box up. So once your query load becomes very high, you can actually point your dashboard to M2 Query, and I'm going to talk about it next. But M2 Query has completely compatible APIs with Prometheus. So you don't have to change anything in your dashboard. You just point your dashboard to M2 Query and suddenly starts to work. So in a lot of other systems, you have to change your query, which we feel like it's like too much of a change for users. Finally, there's a caveat. So this handles your reads, but if your writes ever get too high, you're currently out of luck because then you have to set up this complicated system. So we're working on making that easier, and I'm going to talk about that in the end. Cool. So this is kind of the view of when your reads get really high. So you're still using the M3 coordinator sidecar, and you use M3DB as your remote storage. Now for your queries, you just point your Grafana dashboards, which we're using with Prometheus, to M3 Query. And currently we support PromQL and M3QL internally. We're planning to open source all these so that everybody can use it. And if you do this, you get all the nice properties of M3 Query, which I mentioned earlier. Cool. So now what we have until now is a manageable way to scale out capacity. So M3DB is like a cluster solution. You can add nodes, move nodes from it. You don't have to do manual sharding of your data and things like that. However, you still have this kind of a single node Prometheus bottleneck. So a single instance can hold no matter how efficient you make it, it can hold like up to, let's say, n million time series. And n is like usually a very small number. And it can't be like hundreds of million, for example. It's like very small single number, even on very big machines. So this, for some people who run in production, this gets really nerve-wracking because how do you know you're actually at capacity, right? Like you have to kind of know before you fall over on your Prometheus box, that you need more Prometheus boxes. So figuring that out is hard. Then how do you mitigate that? So you actually have to shard your metrics manually. So you have to say, let's say you set up 2 Prometheus boxes now, then you have to have them scrape different targets. And that's a big manual effort. And then you have to make people change their dashboards because some of their metrics will live on the other one. So this is kind of a bad solution right now. And I'll be clear, this is not like theoretical. We have companies, I'm trying not to name any company here, but there are some companies which are running 185 boxes of Prometheus, for example, and they're managing them individually because each of them has a different config and you have to manage all of them. And they're running it in HA, so they actually have 370. So it becomes really unmanageable pretty quickly. So this is what we propose is the future and which we hope will solve some of the problems. So at the bottom is what I already showed, wherein if you have an application and if the load is pretty low, you can still use Prometheus. You can use the M3 coordinator sidecar process. You can point it to M3DB. For queries, you can choose to query from Prometheus, or you can choose to use our M3 query service, and it works for you. And one day, if you feel that, hey, my scale actually is really high and I can't deal with Prometheus anymore, then you move up, you have your application talk to the collector, and the collector can scale out indefinitely. And the collector will push the metrics to M3 aggregator, which will aggregate them. And again, this is also scaling out independent of the other components. And finally, aggregator will push to M3DB. So essentially, we are trying to open source our whole stack in phases, and this is kind of the final phase. We're not here yet. That's why it says future. So the work we're trying to do today is to make this really easy to set up, because if it's really hard, if you need like engineers working full time on this, then nobody's going to use an open source. That's why even though you can do it today, we don't really propose you do that. We still say go through the Prometheus route because that's extremely simple to set up going forward. But soon you will be able to set up the whole stack pretty easily. So yeah, we have our docs, mailing list for any questions. We actually have a very active Gitters community. So if you need an answer right away, you can just reach out to Gitter and somebody will respond to you. An interesting thing which has started to happen recently is that some customers, some prospective customers of M3DB are now starting to reply other prospective customers of M3DB on Gitter. So which was like pretty interesting to us because now it's not just us who are like supporting, they're like people are now independently starting to support each other. We came up with our blog post recently for M3. We're actually gonna publish a blog post soon about the query engine. That's still in kind of in beta phase. We have the sidecar out in production, but the query engine, which can take in the Grafana dashboards, is still in beta. So now we wanted to launch it through a blog post so that people kind of explain, understand what it does and all the nice properties it has. So keep an eye out for that. It should be out in. Yeah, I think I'm out of time. So thank you for attending the talk.